Section 5.3 Day 1 Conditional Probabilities and Independence. We're going to expand upon the probability rules that we covered in Section 5.2. After this section, you should be able to define what's called a conditional probability, compute conditional probabilities, describe chance behavior with what's known as a tree diagram, and also define what are called independent events. The probability we assign to an event can change if we know that some other event has occurred. This idea is key to many applications of probability. When we are trying to find the probability that one event will happen under the condition that some other event is already known to have happened, we are trying to determine what's known as a conditional probability. Here's the definition. The probability that one event happens, given that another event has already known to have happened, is called a conditional probability. Suppose we know that event A has happened. Then the probability of event B happens, given that A has happened, is denoted by this notation. The bar here is read given that. It can also be read as under the condition that. So this would be read either the probability of B given that A, or the probability of B under the condition that A. Here's an example using a two-way table that you can find on page 314. I'm going to define two events here. The first event we'll call E. E is the grade comes from an engineering and physical science course, and event L will be the grade is lower than a B. You can see from this two-way table all the values are given for liberal arts, engineering, and health and human services. Before I do any calculations, I would probably want to calculate the column and the row totals before I try to find the three things that are given below. The first thing I have to the left there and below is I want to find the probability of L, which would be the probability that a grade is lower than the B. Well, what I would look for is the total number of grades that are below a B and divide it by the total number of grades. In this case, it would be 3656 divided by 10,000, or 0.3656. The second one is read the probability of E given L. So I'm looking for the probability that the grade comes from an engineering and physical science course under the condition that the grade is lower than a B. For this calculation, I would just be looking at the engineering and physical science classes and grades. In this case, I would be looking at the total number of grades that are lower than a B, which is 3,656, and then figure out how many were from the engineering and physical science classes, in this case 800. So when taking 800 divided by 3,656, I end up with 0.2188. So in other words, there's about a 21.88% chance that if I find a grade that's lower than a B, it will have come from an engineering and physical science class. The last thing I'm trying to find is the probability of L given E. This is that I'm trying to find the probability of a grade that is lower than a B, given that the grade comes from an engineering and physical science class. This time the total number of grades will come from the engineering and physical science class, with grades below a B, which is 800, by the 1600, and get 0.50. So 50% of the grades from the engineering and physical science classes are below a B. The knowledge that one event has happened does not change the likelihood that an event will happen. We say the two events are independent. Here's the definition of independent events. If two events A and B are independent, the occurrence of one event has no effect on the chance that the other event will happen. In other words, events A and B are independent if the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. I think it'll be helpful if we look at an example with this one. I have a total of 50 students. I have 23 males and 27 females. And I've looked at which hand is the dominant hand. I want to know if the events of being male and being left-handed are independent. So what I'm going to do is find the probability of being left-handed given that the person is a male. So there are 3 left-handed males divided by a total of 23 males, which is 0.13. And now I'm going to compare this to the probability of being left-handed. The first probability was the probability of A given B. Left-handed given that they were a male. And I'm comparing it to the probability of just being left-handed. In this calculation, the probability of being left-handed will be a total of 7. There are a total of 7 left-handed people out of the 50, which ends up being 0.14. Since these two values are not equal, the two events, being male and being left-handed, are not independent. Back in section 5.2, we learned how to describe a sample space of a chance process. Another way to model a chance behavior that involves a sequence of outcomes is to construct a tree diagram. Consider flipping a coin twice. What is the probability of getting 2 heads? Back in the previous section, we looked at setting up our sample space of head and a head and a tail and a head, and a tail and a tail. Since there were 4 possible outcomes, and each outcome was equally likely, each outcome would have a 1 in 4 chance of occurring. So the probability of getting both heads would be 1/4. Here's how you set up a tree diagram. This is a tree diagram that represents this process. This is your starting point right here. When you toss one of the fair coins, you have 2 potential outcomes: flipping a head or flipping a tail. Each outcome in this case are equally likely to occur, 1/2 and 1/2. Once the first toss has come up as a head, your second toss also has the same 2 options. You can flip a head on the second toss or a tail on the second toss, and again, both outcomes are equally likely to occur. You have a 50-50 chance, or 1 in 2. Once you flipped a tail on the first outcome, you still have the chance of flipping a head or a tail on the second toss. As you can see on the tree diagram, you label the outcomes on here as well as the probabilities. So you can see that another way that we could get a 1 in 4 probability to multiply along the branches of the tree. To flip a head, the first toss would be a 1/2 chance. A head on the second toss would have the same probability of 1/2. So if I just multiply those 2 together, it gives me a probability of 1/4. This leads to the idea of a multiplication along the branches in a tree diagram, and a general method for multiplying and finding the probability of A and B that the 2 events would occur together. Here's our general multiplication rule. The probability that event A and B occur can be found using the general multiplication rule. The probability of A and B occurring will be the probability of A occurring times the probability of B given that A has occurred first. Again, the probability of B given A is the conditional probability that the event B occurs given that A has already happened. Here's another example. Teens with online profiles. The Pew Internet and American Life Project found that 93% of teenagers ages 12 to 17 use the internet, and that 55% of the online teens have posted a profile on a social networking site. What percent of teens are online and have a posted profile? First, I would want to go ahead and set up a tree diagram. And here's what the tree diagram would look like. Notice my first event that is occurring this time is whether the teenager is online or not. So yes, the teenager is online, or no, the teenager is not online. You were given that 93% of teenagers are online, hence this being 0.93. The probability then that this teen would not be online is 0.07, or 7%. These two numbers along these two branches must add up to 1. From this branch then, of yes, the teen is online, 50% of those online teens posted a profile on social networking sites. So you can see where the 55% goes on this tree diagram. Of those students then that are online but do not have a social networking profile, it would be the remaining 45%. These two numbers must add up to 1. Obviously, if a student or a teen is not online, they're not going to have a social profile. So this is why no and no equals 1, and no and then yes for the social profile is 0%. Again, there's my probability of online is 0.93, and the probability of a profile given that they're online is 0.55. So if I'm finding the probability of online and have a profile, I'm going to multiply the probability online, which is the 0.93, times the probability that they have a profile given that they're online first. That's this part of the tree. Since I'm already at this point, given I'm online, I'm actually starting at this point position first, and then knowing that I have a profile would mean I'm along this branch. So you can see it's just a matter of multiplying the 0.93 times the 0.55, which ends up being 0.5115, which then suggests that 51.15% of teens are online and have a posted profile. For example, if you look at page 320, you can look at this tree diagram as well. This is regarding adult internet users. The question is, what percent of all internet users visit video sharing sites? You can see that the adults are divided up into 3 different categories: between 18 and 29, 39 and 40, and 50 plus. The percent of online adult internet users that are between the ages of 18 and 29 is 27%. The percent of 30 to 49-year-olds is 0.45 or 45%, and the percent of 50 and above is 0.28 or 28%. Again, those 3 numbers should all add up to 1. Once the person is known to be from the age group of 18 to 29 years old, there's a probability of 0.7 that they visit video sharing sites. For those within the age group of 30 to 49, there's a 0.51 probability that they visit video sharing sites. And if they're 50 plus, there's only a 0.26% chance that they visit video sharing sites. So notice how I'm looking for the percent of all adult internet users that view video sharing sites or visit video sharing sites. There's 3 places: here, here, and here, where adult internet users view video sharing sites. 1 for each of the 3 age groups we're concerned with. You will notice that the calculations are already there for those 3 probabilities. And again, this number right here, the 0.1890, comes from multiplying along the branches of the tree. The probability that they have video, yes, and they're between 18 and 29 would be 0.27 times 0.7, which is 0.1890. Likewise, the 0.2295 comes from multiplying 0.45 times 0.51, and the 0.0728 comes from multiplying 0.28 times 0.26. To find the total then, I would just add these 3 values together, which would end up being almost 50%, 0.4913. In tomorrow's lesson, we will continue with section 5.3 and we will finish up chapter 5.